Thank you. And I'm joined by Shane Mainali, who's an engineering manager also on Azure Storage. And what we're here to talk about today is how we took our existing exabyte scale object storage system and adapted it to include file system semantics on top of it to support data lake or big data analytics workloads. So let's get started. From an agenda point of view, what we're going to do is we're going to start off with just understanding what data lake systems do and what an analytics workload looks like. After that, we'll talk about Azure Data Lake Storage, which is the service that we built with this file system semantics offering built on top of it. And last, we'll do a deep dive and show you how we've implemented that, and then we'll open it up for question and answers. So I don't know how many of you attended Rebecca Weekly's session on Tuesday where she talked about innovating for the future and the importance of large enterprises implementing data lakes such that they can stay competitive and get insights from the data they're accumulating, right? And so Azure Storage or any type of storage platform is at the heart and center of any of these data lake type implementations. And when you run big data workloads in a data lake, typically there's at least a pattern that you see or a workflow. So let's just touch on what that workflow would look like. But essentially what a data lake is aiming to do is bring data from disparate sources. It can be different scales, different types, different formats from different systems into a centralized store. And so the first part of that is you ingest that data. The second part of that is you prepare that data for processing. And so it might be sanitizing, it could be deduplication, it could be curation, it could be some type of transformation. And what they typically call ETL in the database world is essentially what you're trying to do with that data before you try to go do something with it. The third step is typically some kind of processing. And so two examples would be, I'm trying to aggregate that data so I can put that in a data warehouse. And so I can do some ad hoc querying or reporting out of it. Or I can be training models. And so you're trying to do some kind of ML AI on top of that data. And so that would be step 3. Step 4 is if I'm trying to upload that into a data warehouse, then I put that into some kind of a data warehouse. Or last is I can either offer it up into a real-time application or some kind of a dashboarding tool. So that's typically what you will see in a data lake implementation or a big data analytics workflow, because you're talking about large volumes of data, typically in the order of terabytes and petabytes. But that's the sequence in which the work is typically done. So what are the challenges that we've seen with our customers as they've gone through this process? So typically what you see is, let's take the example of the processing step in that previous diagram. When you take a Hadoop cluster, for example, which is typically what's used to process large volumes of data, you will mount that data into that Hadoop cluster on what we call a file system. And these Hadoop clusters typically will interoperate with the data using file system APIs. So the HDFS APIs are all file system APIs. What we wind up doing is, because the underlying storage platform is an object storage platform, all the file system operations wind up having to be emulated on the client side. And so there's a huge performance implication or impact because of that client-side enumeration. The second thing is directory operations are very expensive. Directory operations are super common in big data analytics workloads. For example, if you're running a huge MapReduce job, while the job is running, all of the data gets put onto a folder. Towards the end, when the job is done, they will rename the folder. And so if you take a really large MapReduce job, well, let's say 10,000 files, at the end of that job, you will be renaming the folder. Under the covers, there's 10,000 files that actually need to be impacted. And I'll walk you through what the challenge is with that pattern. Why does this keep jumping? Okay. And the other thing is, because of the complexity of that platform and different touch points, in typical big data applications, you want fine-grained access control. You don't want the access control at the container level or the account level. You really want that on folders. People will say, hey, I have a department folder or highly sensitive data, and you want to start doing access control on folders, which is very difficult to do in a typical object storage system because it's coarse-grained access control that's possible. So those are the challenges. And so for us, the goals that we have to solve this problem, number one, you've got to address the client-side emulation problem and the performance aspects of that. And so for us, what we wanted to do is we wanted to go and build a hierarchical namespace that will allow us to treat that data using file and folder semantics. So that was the primary goal that we had, and we wanted to go and solve the client-side emulation problem. The second is we did not want customers to have to move data based on the use case. So if they had their data in an object storage platform, we didn't want them to go and create another account and duplicate that data and incur additional cost. And so for us, interoperability of the same data for various use cases was also a design goal. We also, because we're talking about file system semantics, we also wanted to go and support additional protocols outside of just the HDFS, which is for big data analytics. And of course, because we're talking about large volumes, we wanted to design the system for very large throughput. So that's the goals that we had. So let's look at how we went and built this. Interesting. So what you're seeing here is essentially Azure Storage. It's the service that we've offered. It's our object storage platform that we've offered for years. But essentially, it's an object storage platform. We didn't want to go and reinvent the wheel. All we wanted to do was leverage what we've already built, but add on the file system semantics. And so that's what we added. We added a hierarchical namespace on top of our existing object storage platform such that we could reap the benefits of what we already had. The devil's taken over. See, the impatient. OK, I'm going to turn this off, and I'm going to stand by the laptop, and I'm going to go the old-fashioned way. OK. And so what we're trying to do is not reinvent the wheel, no duplicate investments, leverage what we already have and the success that our customers have already had, and layer on top of it, right? And so that's what we did. We wanted to build a hierarchical namespace on top of object storage platform. All right. This is going to be very interesting. And so that's essentially the goal, right? And so I think we can move off to the slide. I think it's getting bored. OK, so let's take an example. If you have a Hadoop cluster, typically you've got the client, which is the Hadoop cluster, interacting with an object storage layer remotely somewhere else, OK? And so let's take that example of a rename folder operation. I've got 10,000 files, and the Hadoop cluster is submitting a rename operation on that folder. What the storage client, which is the Hadoop driver that's talking to the storage system, what that has to do is enumerate all those 10,000 files and submit a rename operation for every single file. That's what traditionally we've had to go and do. What we did now is, since we added the hierarchical namespace, we can now start treating files and folders inside the server. And so when someone wants to do a rename, it's no longer listing 10,000 files. It's essentially saying, slow. It's essentially saying, rename that folder. OK, here's what I'm going to do. No, that I clicked. OK. So what we've done is we've added right next to that object layer, we've added a namespace layer. And the namespace layer is kind of smart. It now stores folders and files. And so what that allows us to do is when the Hadoop cluster says, go and rename a folder, instead of enumerating 10,000 objects, we can say, go change that one folder name. And it's not even an object operation. It's a metadata operation, and it's super fast. Now that we have metadata about files and folders, we can also solve the access control problem. What we can do is we can say, I've got folders, and I've got files, and I want you to start putting metadata against those folders and files. And so we can start doing access control lists at a more fine-grained level. So that's at the high level. This one's more of an example of how we've done that. What you see on the left is the object storage side, where if I had a file, there's one entry in the namespace. Whereas in the hierarchical namespace, I now have one entry for every entity, which is a folder or a file. And so I have 3 entities. And if I want to stick acls on path 2, I can stick acls on path 2. If I want to rename path 3, I can just rename path 3, and it's a very quick metadata operation. So that's the intent of this design, right?
What happens to the underlying namespace of the object side?
So that's a very good question. I'm actually happy that you guys are asking questions in between. But if it takes too long, then we can hold it to the end. But the goal here is, and I spoke about interoperability. So for someone who's just doing object storage workloads, you kind of just go through this path. They don't care about analytics. They don't care about directory operations or fine-grained access control. They just come down through this path, and the flat namespace is existent for that use case. But someone who wants to go down this path, what we've done is we've created the hierarchical namespace. We've allowed those APIs to also go through that namespace, but we still honor all of the acls and all of that. And that's where the true interoperability happens. And so you can either turn it on or off. If you're on, you go down this path, you get all of the benefits, plus you get the fine-grained access control and the folders. If you don't really care about that, you stick to this side. And so you can actually use the same system as an object storage platform and a data lake. So that's the true beauty of this design.
But if only one of them remains valid, and it still remain a directory folder, then the black side becomes invalid and you can't.
You don't even go through the black side if you're on this one. So you're using one or the other. You're not using both at the same time. So there's only one source of truth as far as the account is concerned. And so if you want to map the concepts, we're talking about object storage and file system storage. So if you're trying to map the concepts, you start off with, hey, I have an account. In any cloud storage platform, you have accounts. The accounts are exactly the same. Next, you're talking about a container, which is very similar to a bucket. If you're familiar with AWS, it's very similar to a bucket. In the file system world, you talk about, in the Hadoop analytics world, you talk about that as a file system. It's the exact same thing. I've got a file system, and it's got a bunch of files and folders. I've got a container, it's got a bunch of objects. So those concepts map. Then you talk about directories. So directories is nothing but a special type of object that we store under the cover. So it just maps to an object or a blob. In our service, we call it a blob. And then the files map to objects. So that's the very high-level design that we currently have. And then I'm going to hand it over to Shane. He's going to walk you through how we actually implemented it, and primarily around the performance and the scale aspects of it. And he's actually not going to be possessed because he's going to use the other thing.
Test. All right, there we go. All right. Okay. Hey everyone, my name is Shane Manali. I work on the Azure Storage team with Raji. My team works specifically on big data and analytics and file system storage offerings. So I'm going to talk more about what's under the hood here, especially the file system and hierarchical namespace pieces. If you guys actually attended the talks on Delta FS, either one by Bradley from LAML or Ching from CMU, you'll probably find a lot of conceptual similarities here. Yeah, let's get started. So let's talk about the flat namespace architecture. Before we had the file system semantics, how do things look under the covers? So at the top layer, we have the front end. It's our stateless front door, does all the request parsing, validation, throttling, caching, authentication, authorization, all that stuff you expect the front end to do. And then below that, we have the partition layer. This is our massively scalable key value store. You put a single key, a single full blob path, for example, and you map to a value, a blob. This layer deals with key value store transaction semantics and gives strong consistency for those things. It also deals with automatic load balancing. So it scales out this massive key value store automatically. And then below that, we have the stream layer. The stream layer is dealing with all the media. So the replication of all the bits. If a node goes down, re-replicating those things, erasure coding and journaling, all that kind of stuff is in the stream layer. So this is our architecture without file system semantics. So when we add file system semantics, like Raji said, we add the hierarchical namespace. A customer makes the choice. So a customer, based on their scenario, would choose to enable or disable the hierarchical namespace. So again, big data workloads, file system semantics, they will always enable HNS, which is the hierarchical namespace. And then if they need directory semantics or acls, they have to enable HNS. Where it sits in the architecture is between the front end and the partition layer. So the responsibility of HNS is purely a few things. It's to traverse a namespace and then manage the hierarchy and all the file and directory metadata. It does not deal with anything else. It doesn't deal with blob data, reads and writes. All the blob stuff that we had before in the flat namespace in the object storage world still live just like before. It only deals with the namespace. And then another key point is HNS does not deal with persistence. It leverages the partition layer and stream layers completely for all persistence. So all it has to do is deal with live requests, namespace request serving. That's its job. Okay, so let's talk a little bit more about what is a hierarchical namespace. So the difference between flat and hierarchical, like Raji pointed out, is those having representation for all the parts of a path. So if you look at a flat topology, you'll see that full blob path has a full key, single value, which is the blob. And you don't see any representation for the directories. Whereas in the HNS topology, you see representation for each part of the path. So every directory has an entity that lives in the system, and we have state backing it. The second big part of HNS is the topology. The big piece there is separating the naming from the topology. Because if you want to be able to do a file system things like rename directory, you have to separate the naming from the topology so that when you do the rename directory, you don't have to change all the children in order to do that operation. So that's the two big pieces that HNS is bringing, is representing all the parts of the path and then separating the naming from the topology. So let's talk a little bit more about how we store this structure using the partition layer. So first thing to call out here is the root is sort of special. Raji pointed out the object hierarchy. We have account, file system, directory, and files. The account and file system, those objects have different metadata. And whenever you create a file system, and you can have lots in a single account, we always create the root as a special thing, and we know the root's ID up front. So whenever we go to look into this HNS state, we always have the root ID before going there. So given that, you can see an example here. What we do for the key and the key value store, the first two parts, the account and the file system. That lets us isolate different accounts and file systems from each other. It also effectively gives every file system its own huge namespace. Next, after account and file system, we have the parent ID. So that ID is separating the topology from the name. And then after the parent ID, we have the name of the object itself. And then the way we traverse this structure is the parent ID, the name, and then we have the object ID for that name. So we can then go to the next row we need to go to and keep doing that until we reach the leaf. So this is how we store it in the key value store. Let's talk a little bit about the flow, how do requests flow through the system. So create file request will go to our front end, like any other storage request. It'll then go to an HNS instance. We'll talk a bit more about how we choose which one. And then that will go to the HNS will then see that in this case, none of the parents or anything is created. So it'll prepare all the records to be inserted into the partition layer. So it prepares the top level path 2, then path 3, file 3, and the underlying blob. And then it tells the partition layer to persist all of these things, which in turn talks to the stream layer and persists them on disks. So this is the flow of a create file. Let's also go through a rename directory. So a rename directory, one of the common examples, like Raji mentioned, is we'll see big data jobs running, and they'll have temporary state. And usually there's some temporary name for a top-level folder there. And when the job is finished, it'll rename that directory to some master-like name, and then that's when all the future jobs will read that data. So this is an example of that here. The rename directory is coming to the front end. It is then going to an HNS instance. It sees that path exists. It does a bunch of checks. And then it prepares a single entity update for the path to directory to be changed to master. This is just changing a single name on a single entity. And then it sends that record, like before, to the partition layer, which persisted. So these are kind of two examples, create file and rename directory, and how we leverage the partition layer. So now we've talked a little bit about flow. Let's talk about scale, one of the more meatier topics here. So to talk about scale, one of the first things you have to talk about is a scale unit of storage. What is a scale unit? It's just a collection of nodes, and on those nodes we have components running. In this case, in the Azure Storage scale unit case, we have front ends and partition layer instances and stream layers, and now HNS is also running. One of the things to point out here is we don't have a separation of front end, stream layer, HNS. So we're able to leverage the same nodes to run HNS. And since they're not dealing with persistence, they're using the partition layer for that. All we have to do is really spin them up very quickly to serve namespace requests. So we can use any node we want to do that. So how do we serve HNS requests in the system? We use a component called a namespace processor, or NP. This is what we spin up on all the nodes to serve namespace requests. Each NP is responsible for a range of IDs, those IDs I mentioned earlier. Right here, we're just sort of showing like single numbers. In reality, there's an account, a file system. There's actually multiple IDs. It's a bit more complicated than that, but we're just showing it for a simple example here. So each node has a bunch of these namespace processors, or NPs. And each NP is responsible for a range of IDs. So any request for an ID in that range has to go to that guy. He's the only one who can own it and serve requests for it. So let's take an example where we need to scale out within a single scale unit. So a node gets hot. It got hot because one of the NPs got hot because there are multiple IDs in his range which are hot, have a lot of traffic. And that's, for example, a directory is hot, it's getting a bunch of queries. So this node got hot because it's serving that directory. In this case, what would happen is we have a load balancing system where all the NPs and all the nodes are constantly returning statistics to this thing called NP master. The NP master is always heartbeating with every NP and every node, and every few seconds gets stats. And so it would see in this case that this particular NP is hot because of traffic. So then it would go into a mode where it needs to make a load balancing decision. And in this case, it sees the traffic is too hot for a single node to serve, so it can't just move it to another node. It actually needs to split the traffic up. So then it would look at the stats, which have a sort of mapping of what IDs are hot, the hottest IDs. And based on that, it'll split the ID range. And then it chooses which node to send the traffic to. And so it does that action and splits the two ranges up, and then the traffic is well balanced. So this is kind of really a high level of how we would do this load balancing across these NPs. There's a little bit more to it than that. So there are two big concepts that we're leveraging. These also come from the partition layer. There's leasing, and then there's mapping information. So leasing, each of those ID ranges, we have a lease on them. So an NP that owns it has a lease. And that's what ensures that only one guy can touch that range. Only one guy owns that. Only one NP owns that range. And that lease can be relinquished and taken by somebody else. So that's part of the load balancing process. And then additionally, we have mapping information that for every NP, the range he serves, and then the node that NP is currently on, that is all stored and mapped. And it's a very small amount of state that we cache in all the front ends in any client of HNS. So that lets every client quickly know, for example, when we do a load balancing action, within those seconds, the client will find out that this mapping information is updated, and then it'll go to the new node for the range that got changed. So and this stuff is all things that we've had for many years with the partition layer, even in the flat namespace model. So this is not, a lot of these leasing and mapping information concepts are not new to us. We just leverage them in a different way with HNS. Second mode of scale out that's interesting here is scaling across scale units. What if one scale unit gets too hot so that we can't, there are not enough nodes in that scale unit? In this case, we actually use the same technique that the front-end, partition layer, and stream layer all use to scale out. We just leverage resources from another scale unit in the same Azure region. This works by NP masters in different scale units coordinating, and then the hot scale unit will borrow nodes from another scale unit that's less hot. And then from there, once we have nodes to use, it just becomes like the first case. We can do load balancing across the node that happens to be in another scale unit. Yeah?
So you mentioned splitting objects. What about just the reverse process of merging? Otherwise, you only split and split and split.
Yeah. So we have basically three modes of load balancing. There's offloading, which is basically moving from one guy to another, but not changing the range that's being served. And that can happen if there are multiple NPs in a node, and then like 3 of them are hot, then we can just move 1 or 2 of them around. Then there's splitting, which we covered. And then merging is really only done if that mapping information and stuff gets to be like a little bit harder to cache or kind of cumbersome. Then we do the merging. Otherwise, there's not a very big reason to do merging, although there is a caching-related reason that I'll cover a little bit later that we do it as well. Okay, so that's a lot about cache scale out. Let's talk a little bit about how we process transactions. So now we've covered the top-level architecture, the structure, the flow, and scale. Let's just kind of put these things together and go through a request, how it would flow through HNS. So let's say we just want to traverse a path. Take a really simple example. We traverse a path. Again, we know the route. It's special, so we know what his ID is. So we look up that mapping information. We see that that route ID is on NP1. So we send a request to NP1 to resolve the route, and then look up the next child, which is path 2. He sees that path 2 is on NP7, so then he sends a request to NP7 to resolve path 2 and look up the next child, which is file 1. NP7 sees that the next child is on NP6, sends a request there to resolve file 1. And then NP6 sees it's at the leaf, returns back the underlying blob ID, and then returns back to the NP1, which can return back to the front end. So this is a simple example of resolving, doing a namespace traversal. So this was actually just a simple transaction, just a resolution. Similarly, if we had like a create file in an existing directory, that would be a simple transaction because it's just touching one NP. It's localized to that guy. He can do all the synchronization that's required. We also, of course, have complicated or distributed transactions, as we call them. For example, a rename directory. Let's say for a given directory, we had to scale it out to 3 NPs. And that means that when we do the rename directory, all 3 of those are owning, processing traffic for that directory. So we have to involve all 3 of those NPs in the rename directory process. So that's why it's distributed transaction. So in that case, what we do, I sort of cheated earlier. I didn't talk about some of the core things that we built into the namespace. There are 2 things that we built in. One is transaction timestamps. Those are actually baked in top-down through HNS. So every operation is leveraging a timestamp and creates or using a new timestamp, et cetera. So any operation gets a consistent view of the namespace at any given time. That's the first key thing. So those 3 NPs will have a consistent view that are involved in the rename directory. Second big thing is we leverage a 2-phase commit protocol. So the 3 NPs that are involved in the rename directory, they will actually all prepare the changes to be done. Either they all commit or nothing happens. There's no mixed state. It's all or nothing. And so that's kind of how those are the 2 big things, the transaction timestamp and the 2-phase commit protocol, how we do distributed transactions. So that's a lot about transactions. Another interesting topic here is caching. So just even in this simple example, you actually saw that we just like, a few parts, we hopped around multiple times, right? If you imagine like a depth 30 path, it's a hell of a lot of hopping going on through the system. And the namespace requests are usually not too big. I mean, the given entity is like maybe hundreds of bytes to like low kilobytes. So the hopping is actually relatively expensive. So we do a couple of things for that with caching. So each NP, of course, does the very simple and straightforward caching of caching the things for the ID range it owns. And then, of course, caching anything for like an active transaction. So those things are pretty straightforward. I won't talk that much about it. The second more interesting thing that we do with caching is we cache the result of path resolution. So we don't have to go through all these hops if the path is stable. And we do that by not only leveraging the NPs that own some state, but we can leverage any NP for cache of a file system. We don't have to use the one that own ranges for it. We found this was very important because the cache has to be able to scale separately from the live request serving of the namespace, which is separately from the persistent state. All 3 of those things, and if we need to do different things with scale. And so that's why we enabled serving cache from any NP, even if it's not serving live request for that part of the namespace. Last sort of thing on caching, we also do try to maintain as much affinity as we can. Very important for COGS and efficiency. So, with the load balancing and scale that I mentioned before that we have, what we do actually is we start a file system out effectively in 1 NP served by 1 guy. And that's okay for a few reasons. First, the load balancing operations are very efficient. They're not copying any data. They're only updating mapping information and exchanging leases. There's no data copying happening. So when a failure happens on one node, for example, and the NP has to be served by another node, that's a very quick operation. We're talking about low seconds. So we can handle failure as well, even if we only have 1 NP serving a range. The second part is we can scale out very quickly. And more importantly, we can scale it incrementally. So we can start a file system on 1 NP and then keep adding more and more as much as the workload demands. So that's kind of why we start small, then we get all the good affinity and locality that we can get. And then as we need to scale, we keep scaling out, and some of the affinity will be moved around and more localized, but we need to trade off scale for that affinity. So that's pretty much everything there. So talked about a lot of stuff here. What are some of the key benefits of our HNS design? So first one, again, we start small, and then we grow as we need to. And that lets us retain as much efficiency and performance as we can, and then trade that off for scale based on the workload. And then we can do that because we have very fast and efficient load balancing. And that load balancing, again, no data copies, and we leverage the partition layer. These are concepts we've had in the partition layer for many, many years in Azure Storage. So we are leveraging all those things here. And then another very interesting point is we have to be able to scale out the layers independently. So like some of the HDFS talks that you heard, for example, they're talking about like trillions, billions of trillions of creates per second. But then it was also mentioned that it's like write once, read never. So it just needs tons of creates. Don't need to really read the data. Definitely don't need to cache the data. And as long as we can scale out those creates, it's good enough. So that's one type of workload. But then on the other side of the spectrum, Raji pointed out there are workloads where they have phases. They need multiple things. There's an ingestion phase, needs heavy creates per second and throughput. Then there's a consumption phase, and these things are regular, right? Where the consumption phase needs to have heavy read traffic to the namespace and the data. And then it also needs to leverage caching because it doesn't know how to keep doing path traversals all the time. So we have a mix of workloads. Just those two by themselves, and there are more than two, are quite different. And so scaling these different layers, the cache of HNS, the live request serving of HNS, and then the persistence of HNS, and the blob data, kind of 4 different layers independently, is very important to serve all the different workloads properly. And then last, really key benefit is we're always strongly consistent. We guarantee that all the time. Before we had the hierarchical namespace, we also guaranteed that, so we retained that with HNS. That keeps the applications and customers, as simple as possible. They don't have to do it with any of these really weird consistency issues, like eventual consistency, where you don't know how long it's going to take, like is it up to date or not. Just sort of a huge pain. So we are always strongly consistent, and customers don't have to deal with any of that stuff. That also is what gives us that interoperability that Raji mentioned. What are some of the other things we can do with HNS? I mentioned those timestamps. We leverage those for consistency, but we don't really leverage them anywhere else yet. So we can actually give at arbitrary granularity snapshots of a file system. That's totally possible with the design. And then using those snapshots, you could read back in time for whatever reason, the backup or any other reason, to get a consistent view, like from 6 months ago, of the namespace. And then similarly, we can give consistency across multiple objects. And that's never been possible because in a key value store, you always have the single key, single value. Even if a system is strongly consistent, you can't give consistency across objects. So the hierarchical namespace enables that across multiple objects. So some of the things that have dependencies between objects can start to be consistent then. And then now that we have file system semantics and HNS, we can actually support other file systems. Today we support AWS, Hadoop, and Blobs. There's a wide variety of file systems I'm sure a lot of people here are familiar with. We can support additional ones, and they'll all be strongly consistent and interoperable as well. So that's pretty much all we had. Open for questions. Yeah?
So there is some big difference between the file system semantics and object semantics with kind of modification of the file.
Mm-hmm.
Right? How do you address it?
So there's a few things on that. So some of the interfaces, for example, like Hadoop, they have a sort of a append and flush semantic.
Yeah, a little bit different. But
yeah.
Let's say talking about regular, whatever, SMB file system.
Mm-hmm.
If you do SMB on top of the blob storage,
Yeah.
how do you modify the file?
Yeah. So in Azure Storage, we actually have multiple kinds of blobs, which is sort of good and bad. We have blobs which are sort of two-phase commit. You put blocks and you commit a block list, and the append and flush thing is similar. And then we have blobs which are, you commit when you write. There's no two-phase thing going on. So there's definitely some of that we can leverage. There's also, we do have applications who are kind of using these blobs as two-phase commit for live writes. We have something called append blobs, which are really meant for, at least in an append system, they do a single I/O for each append, and that optimizes this 2 I/O part. So I think a few of those things can definitely be leveraged. Some are being done today, and some aren't, but yeah.
So does this support hardlinks and softlinks?
Well, softlinks are sort of easy because you just have to store metadata. Hardlinks we don't support right now. Certainly can support them. There's been some some work that's been done for disk workloads where we do something very similar, but we don't expose that to the file system today. Yeah.
It wasn't clear to me whether the objects, the underlying data, was equally accessible from both the object interface and the file interface, whether once you created it in this file namespace, it's kind of different from being accessed through the object interface.
Right. So one of the things I may have missed in the architecture part is when a customer enables the hierarchical namespace for a storage account, every request goes through it or none of them do. There's no mixed mode where like some are going through HNS and some are going through flat. Because as soon as we do that mixed mode, we break down the consistency and we can't give it.
Basically, you have data that's in the file system or you have data that's in an object store, but you don't
It's more like if you enabled HNS, then all the requests, both the object store ones and the file system ones, go through the namespace. So we still give you both interfaces. So like, for example, if you had an app that's 10 years old that uses blobs, it's still going to work with the interoperability.
So that picture is saying I can use that full single path name as a flat namespace and go through run.
Right. Right. And if you think about like from a REST API perspective, actually the paths don't really change whether you're in HNS or not HNS. The path is sort of the same. The absolute path is the same.
And then I think my other question was asked by the gentleman up front, I couldn't hear it back here.
Oh.
Was, and I think I sort of heard an answer, was doing like updated in place in the file system, seeking updates.
Mm-hmm.
You have a mode that supports that efficiently.
Kind of. I guess I gave a partial answer, to be probably honest. So there's things in Azure Storage where we do update in place. There's a thing called page blobs, which is a different blob type that we don't today expose to the hierarchical namespace. That gives update in place, so there's definitely an opportunity there that we don't expose it today. And then we do have a lot of applications which are doing update in place by doing two IOs. Basically, they're putting a block, and then they're updating the block list. One of the things that's different about our storage system is a lot of the other cloud storage systems are, when you have this, when you commit a blob, you can't change it in place. But in our object storage system, you actually can. So when you put a block, you can put it anywhere you want. When you put the block list, you decide where it goes. So you can update in place. It just requires two IOs, a put block and a put block list kind of thing. But it works. That works today. Yeah. Yeah.
With the hierarchical namespace, let's say the file data is stored as a blob.
Mm-hmm.
The
Yeah.
name of that blob is some numerical ID, is that correct?
It's some, internal ID, but the customer can't see it.
So if it is accessed through the object storage interface, it will still be that internal ID, not the full path name.
No, that was sort of like the answer to the other gentleman's question. So when you enable HNS, when you enable the hierarchical namespace, then your blob requests, your object store requests effectively, will also go through the namespace. So you still traverse the naming that you gave us when you stored that file. But you are right, under the covers there's some other abstraction going on, but we just don't show that to the customer.
So not even in the blob.
Sorry?
Not even in the blob space.
No, it's all or nothing, and that way we maintain consistency at all times. Yeah.
Another question. So if someone puts an object into HNS through the flat namespace, and they create a path that, for one reason, would be invalid in the file system, like trying to have a file that has directories in it.
Mm-hmm.
You actually see that up front rejected, and then if it's a valid name, you build the HNS structures to support it through the file system as well, that kind of thing.
That's sort of an easy answer because we don't have that problem today. We probably will have that problem if we support additional file systems. But right now, the blob interface and the data lake storage or Hadoop interface, they don't have conflicts in terms of like paths and things like that. So we're able to support pretty much whatever path we need to. That doesn't really cause us a problem today, but it will in the future. Did that answer both the questions? Okay.
So something that I probably didn't realize. So this is not used with Azure Files?
No, this is not used with Azure. So it's a blob and Azure Data Lake Storage offering. Yeah.
Do you support locking of the files, and where do you store that metadata?
Yeah, we support leasing of files today. Internally, we have sort of directories and files, but we only expose leases on files. And that's very similar. The blob leases and the leases work very similar as they did with flat namespace, where there's metadata on a file that has like a lease ID and expiration and some other state, and so we store that metadata in the namespace. One of the things I sort of glossed over with the architecture is any metadata that was on a blob before in a flat namespace world was sort of up-leveled to the hierarchical namespace. So that state is now that metadata is now living in HNS instead of on the blob.
But it's not by range locking.
No, it's not by range locking. And today there's no snare for range locking, but with other file systems, it's going to come into play. Yeah.
Just to elaborate on the previous question, how do you fit with Azure files, and how do you compare with Azure files in terms of capacity, performance, and other permissions and other things?
Today they're sort of orthogonal, to be honest. So one of the things, our sort of first target with HNS was to make sure that Blobs and our Azure Data Lake storage offerings didn't have any data siloing going on. So that's where we started with the interoperability. But it's kind of the mission of no data silos crosses all of storage. So we would be looking into like how we can further expand that so we really have no data silos across any storage offering. But today they're kind of two data silos effectively.
So to answer your question, the capacity is different between the services. Azure Files is not part of this architecture.
Yeah. Sorry.
I'll go. How would you handle data that ages in place? Is there any cost savings, lower tier storage that it can migrate to, et cetera?
Yeah. So we opened up a while ago a preview program for the interoperability that I described. And so that one basically gives you all of the blob, a lot of the blob capabilities, including tiering and lifecycle management. So you can set tiers and objects that are managed by HNS. You can set a lifecycle policy. Lifecycle policy lets you automatically tier things down to a cool or archival storage based on what you set. For example, this directory after 90 days should go to archive storage. So you can do things like that with HNS.
Yeah, so with Azure Storage, there's a premium offering, there's hot, there's cool, there's archive. And so today, and if you remember the first architecture piece that I showed you, it's built on top of Blobs. And so all of those capabilities are already there. We just need to slowly start lighting that up for the HNS. It's not there yet, but it's coming.
Because of the underlying.
Exactly. Because of that architecture, we don't need to redo things, right? And so we just leverage all of the benefits that we already have in S3.
Yeah.
Any restrictions on multiple providers in the same box?
No restrictions, really, more just the interfaces that we have. So the blob interface has the put block and put block list semantics. So it's a kind of two-phase commit thing going on. But with that, you can also update in place. And then the Data Lake storage interface has like really an append and flush. It's append only, just like Hadoop is. And then you flush data when you're ready to flush. Those are the interfaces you can use, but otherwise no restrictions about like how much parallelism. We don't actually put it here, although there's an appendix thing there. We leverage a feature that we have had for some time called high throughput block blob. Really, it's high throughput blob, and that feature basically lets us have whatever the throughput is for your storage account, you can send that to a single blob if you want. That feature basically shards the blocks across a different part of the partition layer, so the blocks in a blob all get their own scale out as well.
So if it's block aligned, spread across lots of nodes?
The customers choose the blocks, so they give us that in the write request. What's that?
Not in Cosmos. Customers don't choose blocks. They write it any offset they want.
That's true. So in like the Data Lake storage example, they do an append operation. For us, it's an append file, and that.
Not append. Just see somewhere and write. You don't have to append.
Well, today if you think about like data analytics oriented, we're mostly coming from a Hadoop standpoint, and in that standpoint, it's all append and flush. There's no like in place, updating a single block. For that, customer has to read the data back and then use put block and put block list. At least today, that's how it has to work. Yeah.
So the namespace entries are stored in blobs.
In the partition layer, not really exactly on blobs. The leaf level is a blob, but the state is just in a key value store, effectively.
Which is built on top of.
Blobs is a type of object that the partition layer is supporting, but the partition layer supports many kinds of objects.
And so you're using some smart data structures to store these namespaces, some smart tree.
Yes. There's a lot of alignment with some of the other talks if you weren't on the DeltaFS talks. I won't give too much details, but there's a lot of alignment there.
So basically, what we did is extending the object storage API to have hierarchical namespace, but not the full file system semantics that file systems usually have.
Yeah, and since we started with Hadoop, like that was, most of our customers a lot of the customer base is coming from a Hadoop standpoint. A lot of the cloud play there, honestly, is from Hadoop. So we started with that. But there will be other file systems that we're going to be looking into to support as well. So we'll get into some of these problems, like update in place and Hardlinks and all this kind of stuff. Yeah.
So you said you are planning to support snapshotting, right?
Mm-hmm.
So are there any changes required to support snapshotting? For example, if I rename a directory, I want to list like 3 months old view.
Mm-hmm.
That directory should be present at the old name, right?
Yeah, there are kind of multiple phases of snapshots though. Today, Blobs already has snapshots, so that's kind of going to be part of our interoperability program that we're running. But that's just a file-only snapshot, so it's a bit easier to deal with. What I talked about, we'll just deal with that automatically. Then there's like directory or files, or there's some other level, higher level snapshot. That will certainly need changes. It's a bit tricky to go over some of the changes that we'll need to do since we haven't exposed any of those things right now, but it will need changes.
And that's what you talked about in the opportunity today.
Yes.
You can now start doing those kind of things, which was not possible on an object storage system.
It wasn't really clear to me what's running in memory on an NT versus what it's looking up. Is there any downside to an NT failing other than it just did an NT master just spinning up a new one?
No, they're downside. There's a few seconds. Okay, thanks. Looks like we're out of time. There's a few seconds of load balancing time, especially for the clients to discover that it's on a new node. But those are absorbed by internal retries, so you kind of see a little bit of a latency blip. So we still don't want the failures to happen all the time, but they don't have a very big cost.
So really the only thing that's in memory on the NT itself is the cache?
The cache and anything for active request, yeah.
So we're out of time.
Yeah.
More than happy to take more questions. Shane and I will be outside, so feel free to swing by and ask us any more questions.
Yes, thank you very
so
much.
Thanks.